So, a very good afternoon to all of you. This will be the last lecture for chemical measure trace and ultra trace analysis. And with this, your advanced material chemistry course will be completed. In this lecture, we have completed all these 5 modules. And here today, we will be looking into these 2 important techniques. So, neutron activation analysis and X-ray fluorescence analysis. Both of these techniques are quite important because they are non-destructive technique. Means you can use directly, your solid sample can be taken for analysis, unlike in all other previous cases where we have seen that our sample needs dissolution with following a proper procedure, which again differs based on the matrix and other aspects we need to take care of while dissolving the samples. But in these 2 cases, we can directly take the solid sample. So before going to the neutron activation analysis, we first need to know what are the atomic notations are. I know you must all have been acquainted with this. For an element, if this is X is its symbol, then this A represents its mass number, which is written on the as a superscript, and this Z is the atomic number, which is written as a subscript on the left hand side. So for example, this is nitrogen. 714 means atomic number is 7 and mass number is 14. So number of neutrons also can be calculated from the mass number minus the atomic number. So that will be the number of neutrons. And now you know there are isotopes, isobars and isotones. So what are they? Isotopes means Z is same, your atomic number is same, with mass number different means number of neutrons are different. Isobars are what? Mass number same, but atomic number can be different. Isotones, number of neutrons same. So these are the various terminologies for a atomic notation. And nuclide, a particular type of nucleus characterized by a specific atomic number and nuclear numbers. And nuclear numbers or mass number is the number of nucleons, that means protons plus neutrons. So these are the atomic notations which are very much important whenever you are looking into either neutron activation or X-ray fluorescence. Again, in neutron activation analysis, radioactivity also is a term. What is radioactivity? It is the spontaneous breakdown of unstable atomic nuclei, releasing energy and particles like alpha, beta, gamma radiations. To achieve stability, is the process called radioactive decay happens. So radioactivity is evaluated using a standard unit known as becquerel and denoted by BQ, very important, and named after the physicist Henry Becquerel. So what is the unit of radioactivity? It is the actually nuclear disintegrations per unit time is what is radioactivity. That is nuclear disintegrations per unit time. Becquerel, 1 becquerel is actually 1 disintegration, nuclear disintegration per second. This is official SI unit, and commonly used in scientific and regular work is curie. 1 curie is this much. 3 into 10 to the power 7 into 10 to the power 10 disintegrations per second. So originally defined based on radium-226 activity, and it is still there in your old literature. So finally the thing is that 1 curie is equal to 3.7 into 10 to the power 10 becquerel. So this thing is very important. You need always to remember this. So now what are the various, when we are talking about nuclear disintegration or nuclear emission, then what are the various particles they are getting emitted from the nucleus are given here as a list. Alpha particles, beta particles, positron, proton, neutron and gamma rays. And you all are aware of this. Here symbols are given. Then their mass number and neutron and atomic number are given. And then how they are representing. The representation is given, and as you know, gamma is a radiation, so it is a electromagnetic radiation. and their single line description of these particles are given here. So beta decay of a neutron, when beta decay is coming out, so this means all these decays are from your nucleus. So as you know, nucleus contains neutron and proton. So from where this beta or positron is coming, those are coming from the neutron. So when beta decay of neutron transfers into it a proton by the emission of an electron accompanied by an antineutrino, and similarly positron emission happens from proton. Proton is converted into a nucleon by the emission of a positron with a neutrino. So these are not the things because they are not a part of any nucleus, but this beta particle are coming by decay of neutron into a positron, and positron are coming by disintegration of your proton to neutron. So these are the things. Now, nuclear analytical techniques. So now let us look into what are the various nuclear analytical techniques. Neutron activation analysis is a generic term. Now, how it is different and what are the various types of it, we will see into it. So now nuclear analytical techniques deals with use of radioisotope tracer or induced activity and measurement of radiation. One is direct method, another is an indirect method. Direct method means the element must be of having natural radioactivity, so that when due to its natural radioactivity on stable nucleus, it will be emitted some nuclear particles like alpha, beta, gamma, positron, neutron, and therefore you can measure those things, and that is the direct method. What is indirect method? Either you can activate your one stable nuclei needs to be activated to give disintegration or all those nuclear particles, and then you can do your measurement. So that is indirect method. Activation methods are prompt gamma, pixie, etc. Delayed in prompt neutron, like whenever you are activating one stable element, so immediately if you want to measure something, then that is prompt gamma neutron activation analysis, and pixie, particle induced X-ray emission, which are immediately happening after activation of the nucleus. And there are delayed process also, in which there is delayed neutron activation analysis, charge particle activation analysis, or proton activation analysis. And there are also ion beam analysis are there, like nuclear reaction analysis, PG, RBS, and PIXI, particle induced X-ray emission. So all these things are there. Rutherford back scattering, and all the things are there. So addition of radio tracers, either you can make in a reactor or you can procure them, and that can be used during your analysis. So that is use of radio tracer to follow various experiments. And then also use of radiation sources. If you are using various radiation sources to activate your element, then that also can be done either by absorption of these particles or any scattering analysis or any fluorescence, XRF, or all the things. So these are the indirect method of analysis. Now, in neutron activation analysis, what is the history is that it is a powerful isotopic specific nuclear analytical technique. See, this is a isotope specific analytical techniques. Whatever techniques till now we have seen, whether it is GCMS, LCMS, AS, or ICP, OES, all those are not isotope specifics. Yes, mass spectrometry is definitely isotope specific, but all the other techniques, whatever you have seen, are not. But now neutron activation analysis is a isotope specific analysis for simultaneous determination of elemental composition of major, minor, and trace elements in diverse matrices. So this is the scientist who and Hilde Levy were the first to introduce Na in 1936. Now this is the picture. Another picture also is there. So you can say this is the Hepse and this is the Levy. She was an assistant to the Hungarian physical chemist George Hepse, and this is the Hepse. So who has won the Nobel Prize of Chemistry in 1943. So these are the two scientists who has found out the neutron activation analysis. Now, in neutron activation analysis, what actually happens has been shown here. You can see it's a nuclear analytical technique for qualitative as well as quantitative element analysis based on neutron-induced nuclear reaction. Means neutron-induced nuclear reaction means there is a target which is bombarded by a neutron, and therefore this has induced instability in the nucleus by forming it a compound nucleus, and then because it is unstable, it will now emit prompt gamma radiation, and again it will, after emitting prompt gamma, it will come to ground state. But because of this neutron, the nucleus is become unstable, and then it will emit either beta particle, and then it will decay to some other compound, and then again decay of gamma radiation, and then it is the ground state. So these are the various processes which are happening in a neutron activation analysis. During this, what we are measuring is the characteristic gamma rays, whether it is prompt gamma or delayed gamma radiation. So these two are the characteristic of the nucleus who are emitting that. It is non-destructive, multi-elemental, high sensitivity, widely used in nuclear, environmental, biological, and all this type of analysis. So prominent mode of interaction, which is very common, is that N-gamma capture reaction. So neutron will be captured by the target element. It becomes unstable, and then it will emit a gamma. Now, neutron interaction often produces radioisotopes. Entire periodic table can be covered by neutron activation analysis. Now, you can see what is the principle. Already I have explained there. The stable nucleus captures a neutron. So this is the reaction. This is a stable nucleus which will be kept like this. This will capture, and then this will emit. Excited nucleus decay to a radioactive nuclide. So now you can see this is the target element. This is the neutron. It will capture, go to the excited state. Then by various decay, it will come to the ground state. Again, because now neutron is added to the nucleus, this will be unstable. It will emit a beta particle, then come to another element will form, and there again some gamma rays will be there. So this is the delayed gamma neutron activation analysis, which is normally known as neutron activation analysis. And if immediately you are measuring the gamma, then that is prompt gamma neutron activation analysis. So nuclear reactions in a common reactions, I have listed it here, though this is the most common one, but other reactions are also there. NP and alpha, and after neutron, you know, all the fission reactions are there, which happens by absorbing a neutron. So neutron fission, and then this is an example I have given. So this is cobalt. Cobalt can be estimated, but these are the gamma energies. So now prompt gamma, Na categories. What are the various categories of Na? Again, Na is the delayed gamma. So Na neutron activation analysis, there is, I have already mentioned it, but again, now it is prompt gamma and delayed gamma. So you can see what is the prompt gamma, what is these features and applications. Applications are mostly non-metals, boron analysis you can do, cement, coal, explosive, and any nuclear materials. Delayed gamma is environmental samples, biological material samples, geological material, etc. You can do. So these are the measurement of delayed gamma, the prompt gamma. So this is the thing. So what is the normal experimental steps while performing a neutron activation analysis? Is that sample preparation and encapsulation, pre-irradiation sample treatments such as cleaning, drying or ashing, pre-concentration of elements of interest or elimination of interfering elements, subsampling and packaging. So these things will come under sample preparation and encapsulation. Those sample, after encapsulating that has to be irradiated with neutron. You can use a reactor, nuclear reactor, or a neutron source. Then radiochemical separation, if required. If something is very highly active, you need to separate those. So if required, then it is radiochemical separation needs to be done, which is known as radiochemical neutron activation analysis. Then you need to cool it Cooling period you need to allow, because now it will be highly activated if the samples contains sodium and all. So they will have a very short half-life, but now the sample will be, after irradiation, it will be highly activated. So you have to wait till all these things completely decays down. That is known as cooling period. And then you need to do the gamma measurement, then use spectrum analysis, and then critical evaluation of results and preparation of your analysis report. So these are the typical steps followed in neutron activation analysis. Some factors to be considered while doing a neutron activation analysis is you need to have a good neutron source. Normally nuclear reactor, high flux has to be there, then maximum low energy neutron component. Other actually fast energy neutron are not get absorbed by the element, so it has to be thermal neutron. So that is the low energy neutrons component should be high. First access to sample, provision for irradiation of different size of samples has to be there. And then high resolution gamma spectrometer, this is all irradiation parameters. And now after irradiation, you need to measure the gamma rays emitted from the sample. So you need to have a high resolution gamma spectrometer. Low background, spectral analysis software, and preferably Compton suppression spectrometer needs to be there, because there's a very high background Compton scattering will be there. So that needs to be suppressed. And then you need to have sample prepare, reproducible sample detector geometry, and you need to look into the quality assurance and quality control parameters throughout the analysis. Now, what can be the sources of neutron? It can be research reactors, like in BRC, you may be knowing Apsara is there, Dhruva is there. Isotopic sources also can be there, which emits neutron. Then neutron generators are there, either deuterium tritium or deuterium neutron generators. So the neutron flux needed is around 10 to the 12 to 10 to the 14, which is obtained in a reactor. Then you can go to very, very low level of detection. If it is not that much higher, then also you can do neutron activation analysis, but then sensitivity will be, or detection limit will be rather poor. So now what is the flux? The flux unit is neutrons, means this much of neutrons per centimeter square, means this is the area per unit area and per unit time. So neutron per centimeter square per second. So this is the thing. So now nuclear reactors, there are very now nuclear reactors, you know, this is either your Apsara or your Dhruva is there. Radioisotopes may either it can be spontaneous fission, for example, californium 252. So 100 milligram of californium will give a usable flux of 2 into 10 to the 9. You can see the flux, it is this much in case of a nuclear reactor, 10 to the power 12 to 14. However, a californium will give 10 to the 9. It is low, but not very much low also. It can be used. Then there is alpha neutron sources also. That means you bombard these things with alpha and they will emit one neutron will be emitted. So they will be the radioactive compounds which will be decaying by giving alpha particle, and your neutron will be emitted from there. These are the gamma neutron sources. And now neutron generator, this is deuterium tritium generator. It works like this. When those two are combining, and then helium will be forming with a neutron of this much MeV energy. And now deuterium also. So this is the reaction for neutron generators. Now these are the typical pictures for various research reactor facility. This is Apsara, Dhruva, Cyrus, and this is the Kamini reactor, and this is the upgraded Apsara. Right now, what is where the samples are being irradiated. So there's a pneumatic carrier facility in Dhruva or Cyrus. Flux is 10 to the 13 neutron per centimeter square per second. Apsara reactor, the flux is around 10 to the 11. Cyrus and Dhruva flux is again 10 to the 13 to 14. Thermal column of Apsara reactor, it is 8. And so Kamini reactor maximum is 10 to the 12. So these are the various neutron fluxes. Just for your general knowledge, it has been given here. Now, once you have been irradiated, the samples are being irradiated in a reactor. Now, what is the equation which is dealing, like how you are going to calculate the concentration? Is that this is the equation? So here you can see, now this is the activity generated in your sample after irradiation. Now n is the number of your atoms in the target which you are going to calculate after getting all this parameter, because now activity you are going to measure by your detector. Flux is known. Sigma is the neutron absorption cross section, that is known. This is the flux, it is known. And then lambda is the decay constant of radioisotope form, that is also known. So these are the various things which are known, and from this you need to calculate this. All these are known parameters. This is measured by your detector, and now this is the your number of atoms from which you can calculate the concentration. So now N is the Avogadro constant. These are the things you can just see it. Sensitivity depends mainly on activity, and this is the neutron absorption cross section and neutron flux. So how much low you can measure by neutron activation analysis depends on these three parameters. One is the activity generated, and activity generated in tons depends upon the neutron absorption cross section of your element and the flux of your nuclear reactor. So this is the thing. Now what is the CT and LT? CT is the counting time, actual real time during which gamma rays from the samples are counted. So now the unit is second. What is this physical meaning of actual real time during which gamma rays from the samples are counted? Is that this represents the duration over which the radioactive decay events are recorded. Means actually your detector will be in between during measurement of two incoming radiations. There will be some dead time. So it is that factor, and it corrects the decay of radioactive nuclei during your counting, because you need to consider the dead time of the detector. The counting time total. So effective time during the detector is available for record pulses. So these two are actually related term, though not equal, but it is a related term. So during high count rates, the detector experiences dead time. So dead time period is equal to period when detector is busy processing previous events, and hence normally lifetime is less than the counting time. Means counting time is the real time during which counting is done, but because of the dead time, so your actual time will be less. So now this multi-element analysis of samples can be done by neutron activation analysis. You can see I have listed here some detection limits by neutron activation analysis. These are the europium, dysprosium, indium. So it's around detection limit is 10 to the minus 13 to minus 12, and gram, that means you know that 10 to the minus 9 gram is ppb. So now it can go to ppt level you can measure. So now also you can ppt to ppq level you can go. Here also ppt. Now you can see the various detection limits. Quite very good detection limit for almost all the elements can be observed by neutron activation analysis. So values depend on, again, the detection limit values, as I have told you, depends on flux, detection efficiency, sample matrix, and irradiation time. So these detection limits have been calculated based on reactor irradiation of the sample, that means 13 neutron per centimeter square per second neutron flux, and 20% relative efficiency of SPG detector. So now you can have a look just for general knowledge. These are the things which are the element which can be do by your neutron activation analysis. The red mark are for prompt gamma, they can be measured by prompt gamma neutron activation analysis. Now these all the pink, whatever is been written, they are instrumental neutron activation analysis. Then the blue color, here these two are blue color, the fast neutron activation analysis. Because you know, in a nuclear reactor, the moderator is there which slows down or reduce the energy of neutron. So when there is no moderator, like it is a fast reactor, there you can do nitrogen and oxygen. In all other case, you cannot do this too. So this is the just typical for your ready reference, a table given here. So now instrumental versus radiochemical or chemical neutron activation analysis. So it is generally possible to simultaneously measure more than 30 elements in most samples. Like one time you irradiate, you can do more than 30 elements in the same sample which has been irradiated without any chemical processing. So that is instrumental neutron activation analysis, or INAA. So there is no requirement of chemical processing. The application of purely instrumental procedure is commonly called instrumental neutron activation analysis and is one of NA's most important advantages over other analytical techniques, because if you need not process the sample, means there will be no blank. Because you know that blank contribution is coming from processing of samples, and because of the blank, your detection limit is restricted in a particular instrument. So since in neutron activation analysis, more than 30 elements are there which can be done without processing, so blank can be controlled. If chemical separations are done to samples after irradiation to remove interference or to concentrate the radioisotopes of interest, the technique is called as radiochemical neutron activation analysis. So irradiation has been done, and after that you are processing for pre-concentration. So it is radiochemical, means once activity has been generated and then you are doing some chemical processing. So radiochemical neutron activation analysis. And if you are doing the chemical separations before irradiation to remove interference, then it is called as chemical neutron activation analysis. So now let us see a typical example. Say you need to see some, this is the plant sample, this is a plant sample you need to analyze. Then what you will do is, so now you obtain the plant sample. Now, you know, if plant, you have taken this sample from a tree, from a roadside, then you must be aware that lot of dust particles will be there in that. So if you want to know actually what is the components in this piece of sample, then you have to first wash it completely, remove all the contaminants from the surface, and then you have to dry. You have to dehydrate the sample, because now a lot of water content is there. So dehydrate the sample. Dehydration method use are heat or freeze drying, or is frequently used. For the freeze dry method, a plant sample is then placed in the chamber atop the lyophilizer to the right. So this is the just shown. But the thing is that you have to dehydrate the sample, means you need to expel all the moisture from it. Then you have to powder the sample. So definitely you have to wear a gloves and use a clean and dry mortar pestle to powder it. Once you have powdered it, you have to pack the sample in this type of polythene bags, and you have to doubly pack it, double baggage, and then label it. Now select a suitable standard also, because this also here you can do without a standard, but it is always better to have a standard, because if you are taking a standard, then neutron flux and there any variation in neutron flux or anything is there, that gets nullified. Okay, so you have to take a standard. It is always better to take a standard, to select a standard for comparison. Then now you can see, just I have seen you how to pack in a place packages of both the prepared sample and the standard sample in a capsule. So this is a capsule. Keeping up a scale here just to show you how big is the capsule. It is around 2 inch. This is 1 inch and 2 inch of height. You have to give both the sample and standard. You have to pack both the sample and standard in this capsule. So now take the sample to the rapid system of the apparatus. So this is what is shown here is the pneumatic carrier facility of Dhruva reactor. So now you have to pack it in the system, and then the pneumatic carrier will take it to the for irradiation. Now after irradiation of the sample in the capsule, and before removing it from the reactor site, it must be determined if the capsule is safe for transfer. So a GM counter will be there. They will be used to see whether any radioactivity is there present in the sample, and then you have to pack it and bring it to your laboratory for counting. So now the instrumentation used to measure gamma rays from radioactive samples generally consists of a semiconductor detector, associated electronics, and a computer-based multi-channel analyzer. So these are the part of detectors, where the actual detector is a semiconductor detector, and most NA labs operates one or more high-purity germanium detector. SPGE is the most usable type of detector. So now again, methodology of NA, as I have already explained you, NA can be of 3 types like instrumental, radiochemical, and chemical. It is non-destructive, free from blank. The instrumental radioactive and instrumental neutron activation analysis, non-destructive, free from reagent blank, fast and simple. Examples are trace elements in leaf, which I have just explained you. Disadvantages are matrix interference, high matrix activity, because as I have told you, if sodium, which is a integral part of your leaf and all, so sodium is there, then it creates very high activity. So you need to allow your sample to cool down. Determination of traces of cobalt in soil samples, determination of gold in geological samples are the example which can be done by this. However, samples like this, barium, antimony in gunshot residues, which is a forensic importance, or rare earth elements in uranium, need to be done by matrix separation is essential. So this simple INA cannot be done. How matrix separation can be done? It can be either before irradiation or after irradiation. If you are doing it before irradiation, then it is chemical neutron activation analysis. If you are doing it after irradiation, then this is radiochemical neutron activation analysis. This I am repeating it so that you will remember this forever. So what is radiochemical neutron activation analysis means? Separation after irradiation. Example is barium and antimony in gunshot residue. Gunshot residue irradiation is done, radiochemical separation of barium and antimony by precipitation. You can separate barium and antimony by precipitation and then measure the gamma activity. Why it need to be separated? Because gunshot residue contains all these elements in high concentration. They have very strong gamma ray intensity, so that will cause interference. Barium and antimony are present at trace and ultra trace level. So among these high energy gamma rays, finding these two are very, it will be difficult. And there are also overlapping gamma lines will be there, and therefore high background in normal instrumental neutron activation analysis, so which can be avoided by doing the radiochemical separation. And since you are doing radiochemical separation, means if anything is coming from the environment, that will be not active, so it will not create any blank. So that is the importance of radiochemical separation, because no blank can be introduced, because already the sample has been irradiated and whatever elements you are going to analyze are already in activated state. Advantage: free from reagent blank, free from interferences due to matrix and other elements. So you can achieve a very good or better detection limit. Disadvantage is handling of high activity. So because it is a radiochemical separation, so after irradiation you are separating. So now your sample is in active state. So you need to handle very high activity. Now chemical neutron activation analysis, again, to pre-concentrate your sample, you need to do it. If your sample, the concentration of your analyte is in say sub ppb or ppt or ppq range, then you can do some pre-concentration technique which we have already seen before, like solvent extraction, ion exchange, or anything. You need to do take that, and the interferences due to matrix is minimized because you are now separating the matrix. So low active, and then you are separating before irradiation and therefore not handling any radiation. So activity handling is low. Example, impurities in uranium, separation impurities, irradiation, gamma activity measurement. These are the steps. You separate the impurity, irradiate, then do gamma activity measurements. So these are free from interferences due to matrix of uranium. You will not be having any interference because you are already separating it. So disadvantage is that not free from reagent blend, because here you are doing all the procedure before irradiation. So if anything is introduced from the environment, then they can contribute to your blend. So you have to carefully minimize the blend. Now let us see the various advantages and limitations. So it is a multi-elemental technique. Yes, it is a multi-elemental technique, non-destructive, then high accuracy and precision, minimal sample preparation, excellent trace level sensitivity, and matrix independent. But there are some limitations also. Requires nuclear reactor and nucleon source, radioactive waste generated, long analysis time, because if sometimes you need cooling state, then you have to wait for days together to cool the activity of the unwanted elements. Then limited availability and high cost, because getting a nuclear reactor everywhere or nucleon source everywhere is not possible, and not suitable for few elements like your lead and cadmium, which do not form any radioactive element to produce gamma rays for detection. So there is the limitations. Now again, apart from INA, CNA or RNA, the standards used, based on the standard used or standard you are not using, there are various type of methods. One is absolute method, where the concentration is calculated directly using nuclear parameters, because you know all the nuclear parameters are fixed. And now for analyte, the neutron absorption cross section is fixed, flux is fixed. If we are taking a particular reactor, then this kinetic parameter is fixed, then gamma ray is fixed, gamma ray energy is fixed, and this the energy, this epsilon, this is also fixed. So all these things are fixed because now you are using a particular detector, so its efficiency is also fixed. So now if everything is fixed, so you can calculate this measured activity is also, it is given by your detector. So using all these things, you can calculate your N. So that is what the, and indirectly your number of target atoms, if you are calculating, then you can calculate the concentration. So this is the absolute method. But normally you never use absolute method, you always use comparative method. Sample and standards of known concentration are irradiated and counted under identical conditions. Elemental concentrations obtained by ratio of activities, no need for nuclear constants, most accurate and widely used. So it is there. There is another thing, it is a K0. Now K0 standardization method is also there. Usually K0 factor, composite nuclear constant, requires irradiation of only a single comparator. Normally gold is taken. Eliminates the need for multi-elemental standards. So it is key point is high accuracy, internationally standardized, and hence you can use it, suitable for routine multi-elemental NA. So these are the various, how you are calculating, it is written here. And these are the explanation of the various parameters. So now application of NA, you can see I have made this picture here just to show you where all the neutron activation and analysis works. Like not a single field is left out. You can have a look. It covers all the fields starting from biology, forensic science, healthcare, chemical sciences, archaeology, environment, material science, geology, and nuclear technology. Everywhere neutron activation application is. Neutron activation analysis is widely used, and for archaeological things it is a boon because you don't need to decompose your sample and it is totally non-destructive. One example I want to give here, the arsenic entering the human body is incorporated into hair during keratin formation at the follicle and moves along the hair shaft as it grows. Like your hair grows 0.3 to 0.4 millimeter per day, and arsenic, if it is getting trapped in your hair, then it also will be growing at that rate. And so here thus serves as a chronological record of exposure of arsenic. And arsenic is done by INAA, that is instrumental neutron activation analysis. Following this reaction, the characteristic gamma rays from arsenic 76 are measured using SPGE gamma spectrometry for quantification. Now these are the methodology. Wash the hair sample, irradiate in nuclear reactor, count the gamma rays, and you can calculate the arsenic concentration. Now the interpretation is that normal background level is less than 0.2. If someone has arsenic poisoning or arsenic exposure because of its occupational exposure or anything, then your concentration must be beyond 1 ppm. So in case of poisoning or severe exposure, it has to be 5 to 10 ppm or higher. And you have to do the segmental analysis of your hair so that you can connect it to the poisoning time, like before how many years or how many months the poison has been given to somebody. So it has very high forensic significance. One thing I just want to tell, the confirms arsenic exposure, differentiate acute versus chronic intake, and then useful in postmortem investigations. So like long back in the history, it is there that hair of Emperor Napoleon had shown arsenic concentration of 10 microgram per gram, so which indicates that there is poisoning of arsenic to Napoleon. Though it is not been confirmed, but history says that Napoleon has been poisoned by arsenic and which became its cause of death. So this is all because of neutron activation analysis, we can know that. So now the second technique is like analysis of, if you are analysis of some custom samples, if you can see, then either you can do it by EDXRF, NA or XRD, unknown sample. So now some unknown sample has been caught in custom and has been sent for analysis. Actually, what was that? So from EDXRF, then NA, and then XRD pattern, we came to know that it is the iridium metal, which is a noble metal and was being smuggled, which has been caught because of the analysis report. It has been submitted to custom and they can seize it. Now in Gunshot residue analysis, so this is a typical spectra of neutron activation. Gamma spectrum using SPD detector is a typical spectra. You can see this antimony, zinc, barium, then antimony, various lines are there. So this is a Gunshot residue spectra. You can just have a look to this. Now again, gamma spectrum are two neutron irradiated toneric samples, because sometimes the forging in documents is done because somebody may prepare a false document and which sometimes we need to analyze the document which is a requirement of forensic purpose. So now the ink used by different documents can be analyzed and can be found out that they are part of the same document or they are being false documents. So you can find out that. So now geological samples also can be done by neutron activation analysis and see. So these are the gold analysis in some geological sample of Karnataka region. Now these are the three techniques which have been used in instrumental neutron activation, radiochemical and chemical. So you can see there is a clear surge when you are doing a chemical neutron activation analysis, because here the separation is done before activation and hence blank has been contributed, and you can see these two are very closely matching. However, this is slightly increased value, and that may be because of the chemical neutron activation analysis and because of introduction of blank. Now next is the X-ray fluorescence spectrometry. So this is all about neutron activation analysis and few examples I have given. Now let us see what is the X-ray XRF technique or X-ray fluorescence spectrometry. So you know X-ray is also a part of your electromagnetic radiation. After gamma, it comes the X-ray. Gamma rays of nuclear origin, whereas X-ray are of electronic origin. X-rays are a small part of electromagnetic radiation. These are short wavelength electromagnetic radiations produced by deceleration of energetic electrons and or the electronic transitions within the atomic orbitals. X-ray propagates at the velocity of light. As you know, all the electromagnetic radiations propagates at the velocity of light. Their wavelengths range from 10 nanometer to 1 femtometer, and these are the wavelengths or range shown here. This is the wavelength, energy, and frequency of X-rays. Now the X-ray again has been found out by Roentgen and Henry Moseley. So these are the two scientists who the credit of XRF goes to them. So the basic qualitative and quantitative X-ray spectrochemical analysis was established by Moseley in 1930. Now the basic principle of X-ray fluorescence spectrometry is that XRF is it is a non-destructive technique used to determine the elemental composition of materials. So now excitation is there. So what are the three different stages are there in your analysis? A high energy X-ray source irradiates the sample, causing the inner cell electron in the atoms to be ejected. So that is photoelectric effect. Then emission of characteristic X-rays. The removal of inner electron creates vacancies, which are then filled by outer cell electrons. Now this transition releases energy in the form of X-rays that are characteristic of the element present. So this is the basic point, characteristic of the element present, and based on that energy we can identify the element, and based on the intensity of the energy we can quantify the element. So these are the two things. Now we can detect those energy whatever been emitted out. The emitted characteristic X-rays are detected and analyzed to determine the energy and intensity which corresponds to the types and amounts of elements in the sample. Now characteristic X-rays are detected. Okay, so energy in keV or of gamma rays identifies the elements. Intensity of X-rays quantifies the elements. So as I have told you, the energy of X-rays identifies and intensity of X-rays quantifies the elements. This is a typical figure for showing the emission of X-rays, and the typical block diagram of an X-ray fluorescence instrument. So there is a X-ray source. Your sample is kept here. Then this is the detector, preamplifier, and digital pulse processor, and finally your computer or your signal processing unit. What can be the sources? It is usually an X-ray tube Now, sample holder can be different based on your types of samples. It can hold powder, solid, or liquid samples. Detectors measure the characteristic X-rays. For example, silicon dip detector is used in this case. And processing unit, it converts the X-ray signal to spectra for analysis. So you have to convert the X-ray signal into your spectra or intensity. So this is how your processing unit works. Now, what are the X-ray tubes? Normally, most common source is high intensity and versatile. So X-ray tubes are the most common source of X-rays and X-rays. These are high intensity and versatile. The working principle is that electrons are accelerated from a cathode to strike a metal anode, generating X-rays. Now, target material, typically the target material on which electron is bombarded to produce X-rays can be copper, molybdenum, tungsten, rhodium, and silver. So the choice of anode material depends on the application. Advantages is adjustable power output and long lasting and efficient, and disadvantage is requires a high voltage power supply. So everything, when there are some advantages, there are some disadvantages also, and therefore the evaluation process is continuous. So now this is the disadvantages. So now radioisotopes also can be used as sources. For example, americium or iron 55, cadmium, cobalt, all these things of their radioactive isotopes can also be used as an X-ray source. Here radioactive decay produces X-rays of specific energy, and they're used in portable or low power instruments for specific measurements. So since it is portable, you can take them to field for use. So in field instruments can be worked on this principle. So advantage is compact and cost effective, no external power needed, and therefore it can be very well used in field. So limited lifespan due to decay, strict regulatory handling requirements are there because this is containing a radioactive element. So there are very strict regulation to handle the instrument. The third one is the synchrotron radiation source. Now the working principle is relativistic electrons circulating in a synchrotron emit intense, highly collimated X-rays as a result of centripetal acceleration caused by bending of magnets. So in this scale, this is used for advanced research requiring high resolution analysis because here the source is highly intense, and this, if you are using a synchrotron source, then you can very much go up to ppb to ppt level of detection limit. Otherwise, in normal cases, XRF only can measure up to ppm level. So extremely high intensity and tunable energy, ideal for detecting trace and ultra trace element. Disadvantages are again expensive and require specialized facilities. So everywhere it cannot be there. Even in BRC, it is there in CAT Indore only. From where we normally go for if we want to do some our X-ray measurements using synchrotron radiation, then we need to book the beam line, and then after pre-booking the beam line, then only we can go to CAT Indore and do our experiments and come back. So key consideration when choosing an X-ray source is that elemental range. It is selected based on the element of interest, sample type, instrument type. So these are the various things. Now let us see briefly into the sample holders. So as I have told you, depending on your type of sample, so that the solid sample, liquid sample, or powder sample, you are having different type of sample holders. Solid sample uses flat, rigid samples like metal, ceramic, or rock, usually made up of inert material. Secure the sample to prevent movement during analysis. Applications analysis of metals and alloy, coins, and geological samples. A circular sample holder for pressed pellet or soil or powder. Like sometimes it is a powder sample, then you can make pellet out of it so that you can place the pellet there and your analysis will be done easily. There can also be powder sample holder if you like your sample is not you cannot bind it to a pellet, then directly powder sample also can be done. So designed for powder samples like ore, cement, pharmaceuticals. Powders are pressed into a pellet using a hydraulic press. Even if you are not pressing it, you can directly take the powder sample. Alternately, powders can be placed in a cup with a support film, the mylar or polypropylene. Application is elemental analysis in powder materials. Now, liquid sample holder also is there, which is like directly your organic or aqueous sample. You can take specialized cells with thin X-ray transparent film, mylar or Kapton, prevents spillage and evaporation during analysis. Application is that analysis of heavy metals in water or trace elements in biological fluids. Also, thin film sample holders are there for thin film or coatings on substrate. So, these type of holders are used. Rotating sample holder, right here, if you have put multiple sample or you want to focus different point of a particular sample, then this is the case. The rotating sample holder, it rotates the sample during analysis to improve signal homogeneity. You can measure at 10 different points of your sample and then you can average it out. Now, application is useful for inhomogeneous or large area samples. Now, what are the factors based on which you need to select a sample holder? Is that the state of sample? Definitely, it is true, like solid, powder, liquid, or film. You have to ensure even X-ray exposure across the sample. Must be chemically inert to avoid contamination reaction with the sample, and transparent to X-rays. So whatever sample holder material is there, it should not absorb the X-ray itself, otherwise it will mislead you. So it should be transparent to X-ray. So materials like mylar or Kapton are used to minimize X-ray attenuation. So these are the. Now what are the detectors in case of X-ray? The gas field detector or proportional counter. Now I have given you a principle also. It detects X-ray by what is the principle? It will ionize the gas molecule in the detector chamber. Advantage is fast response time and cost effective. Limitation is low energy resolution, best suited for wavelength, and dispersive XRF or WD XRF is there, but it is not easy for EDXRF. Scintillation detector, the principle converts X-ray into light via a scintillator. For example, sodium iodide thallium, which is then detected by a photomultiplier tube. What is the advantage? Is high sensitivity for higher energy X-rays, and limitations are limited energy resolution, mostly used for in WDXRF detecting higher energy X-rays. Semiconductor detectors. So all these are applicable for EDXRF. The previous two are mostly suitable for WDXRF and this is suitable for EDXRF. You can see the semiconductor detectors and whatever is having in our division, that is also having a semiconductor detector. So silicon dip detector, SDD, X-ray creates electron hole pair in silicon which are collected and measured. Advantage is excellent energy resolution around 120 to 150 electron volt. Fast response and ideal for energy dispersive XRF. Application is for trace element analysis, environmental studies, industrial applications. There is another one, lithium, like example is lithium drifted silicon detectors also. So similar to STD, but uses lithium to improve sensitivity. It requires cooling to a liquid nitrogen temperature for operation because lithium is there. Again, cadmium telluride detectors are also there and multi-channel analyzers are also there. So I have written down in short all those detectors, the principle, advantages and application. You can just have a look and you can understand it. So now a typical, I have given a comparison table here. So if there are different types of detectors, what is their resolution, energy range, advantages and limitations? For this, I have just made a table from which just with one look you can know the capabilities and shortcomings of each detectors. So normally this detector is used widely in EDXRF. Now let us see the advantages and then disadvantages. of XRF. Again, advantage one, the most important advantage is it is a non-destructive analysis for which this can help, like you can like the various gemstones or historical artifacts or artifacts from your museum and all can be done by this. Rapid and simple operation, wide elemental range, versatile sample type, quantitative and qualitative analysis both can be done, high sensitivity and precision, minimal waste generation, and automation and portability. Like you can have portable XRF for the field use also when you are using your normal radioactive element as the source, and long-term stability. But still, as I have told you, disadvantages are also long because you have matrix effect, limited detection for light element, you need to vacuum it. Elements are lighter like than sodium, for example, hydrogen, helium, lithium are difficult to detect due to low fluorescence yield. Special systems like helium purge or vacuum chambers may be required. They are there in many cases, you can do it, but still you cannot go to very low level. Matrix effect is there because if your sample, your elemental signals can be influenced by the sample matrix, leading to potential inaccuracies. So it requires a matrix mesh standard for correction. And as you may be knowing, a perfectly matrix mesh standards is very much difficult to arrange. And it is surface analysis technique because now your X-rays are falling on the sample. They do not have that power to go deep inside. And it is normally only a few micrometer of the sample can be handled. Lower sensitivity for trace elements compared to other techniques like ICP-MS. It has like low sensitivity or detection limit is bit poorer than ICP-MS. Cost of instrument is high, very high initial cost for advanced XRF. Instruments, maintenance and consumables are also expensive. Interferences, overlapping peaks in the spectra, request deep convolution algorithms or advanced detection is required. So sample preparation for powders are also very much difficult. You have to pellet it normally, or you need to create a fused bit if you feel that the samples are not very homogeneous or the pellet is not sustaining, then you have to fuse it to make a fusion bed, and then you can analyze it. And since you are handling X-ray, it poses a potential safety hazard, so one should be careful. Not suitable for organic compound because XRF provides elemental analysis and cannot identify molecular or structural information about organic compounds. It is purely a elemental analysis type of system. So this is all about today's lecture, and this is the upgraded Apsara picture. I have put it here just to show you how it looks like. It is a pool type reactor which is now widely used for our sample irradiation. So now it's all about all the lectures, and in few days I think your assignment will be sent to you. Once HBNI will instruct us, we will send you the assignments and evaluation will be there. So all the questions will be definitely from the slides provided to you. I'll be restrict into that.
And when will be Viva, ma'am?
Once your all the assignment will be submitted by you, then after that the Viva date will be decided by HBNI.
Okay, thank you.
Okay.